Okay, so I think uh, this is the interesting part of the quantum machine learning is quantum deep learning. So just a generic sort of summary of it over here.
So these are fun methods for quantum learning that are quantum machine learning that are based solely on linear algebra.
So in general, when they say quantum machine learning, it can be a number of different things. Some of them try to use noisy quantum computers with continuous classical feedback in order to try to speed up training. So certain training calculations, like loss calculation or adjusting weights, are exponentially faster than the classical versions. But of course, once you take the entire circuit into account, I don't know what the result will be. But that was when they were trying to push the old quantum computers, and maybe still try to push, the next 10 years, how do you make quantum computers assist or provide assistance to classical machine learning. And then in this course, there was a little slice in which they spoke about, if you're dealing with true quantum computers, so perfect quantum computers with the quantum Fourier transform, things like that. And again, there was these examples like sparse matrices and things like that, which are exponentially faster to do with a quantum computer, perfect quantum computer, if we ever get one. But again, it's like in the training, how do you speed up the training? The inference would still be, you're still helping to train a classical machine learning system, and the inference would be classical. So this final last couple of minutes is where what I'm actually interested in.
But then we can also look at other classical machine learning methods, such as deep learning.
Right.
Deep learning, when I first heard about it, I said, wow, this is amazing. Classical computers are going to teach us about deep things about the world, like truth and love and happiness and how to get a date on Saturday night. Mm-hmm. But no, I'm afraid it's not like that. What deep learning means is that you have a deep network where things are interacting with each other.
Right.
I'm just drawing this network. These are lines, are just bits, if you like. Here are things interacting with each other. They should look blobby because it should look a bit like a set of neurons and things. And then you have weights that tell you the responses of these different artificial neurons that are processing these signals. And the idea is that
so over here it looks like he's drawing the network going down as opposed to from left to right as typically is done. So this is more of, I'm guessing, the transformer sort of architecture where it's going down and then it feeds up, down, up, down, up.
If you adjust these rates properly, then if somebody puts in a scrawled 7 into the input of this circuit, which I've drawn at the bottom, at the top, one of these neurons fires that says, oh, it's a 7.
All right, so it's going from down to up.
This is the basis for a huge amount of deep learning protocols, including voice recognition software.
Right, and so it's not a transformer, sorry, it's just inference.
Handwriting recognition software. People basically, if they have any problem, they don't understand it these days, they say, let's whip out the deep neural network and give it a ride. So the interesting thing about deep learning, one of the reasons why it's so effective is that you can show that such deep neural circuits actually can encode any kind of classical logic operation in them. They're effectively computationally universal. This has been known since McCulloch and Pitts, who first introduced these deep artificial neural networks back in the 1940s.
Right.
But if we actually make this quantum mechanical,
okay,
so we have deep quantum learning. So all of our circuits now represent quantum logic gates. The parameters, these weights, which we can adjust to represent the parameters of these gates. Then now, and the things that we put in are quantum states. The outputs themselves are also quantum states. This is how you make something quantum mechanical. You put this funny thing called a Dirac bracket around it. So a good way to make something like Google quantum mechanical is to put these brackets around it. This, by the way, is the logo for the Google.
So essentially what he's saying is that analogous to current deep learning, way down in the future when we have this many resources readily available for qubits and quantum RAM and such, then you can perform, or you can train a quantum deep learning circuit to perform any quantum computation. It should be able to perform any quantum computation just by training it in the same way that you train a classical algorithm. And I'm guessing hopefully it should be able to find the most efficient way of doing so. So this is, I like thinking about this stuff. It's interesting to me.
Google Quantum Artificial Intelligence Group. If you make this into a quantum mechanical deep learning circuit, then this deep learning circuit inherits all the virtues of quantum computing. So we know that it's capable of computing things that cannot be computed classically. For example, these kinds of problems up here. So we know that there are problems that you could learn in a deep quantum learning circuit that you couldn't possibly learn in a deep classical learning circuit. So let me just conclude by saying quantum mechanics is weird. Quantum systems can generate weird patterns that are very hard to generate classically. But quantum systems can also learn and recognize weird patterns that can't be recognized classically. And the reason that they can do this is that quantum computing and quantum mechanics is all about linear algebra. But with a very small number of quantum bits, you can have states that represent vectors in a very high dimensional vector space. And then quantum computers can be used to do linear algebraic operations such as fast Fourier transforms, finding eigenvectors and eigenvalues, and inverting matrices exponentially faster than you can do classically. And I'm very much looking forward to the time in the very near future, I suspect within the next 2 to 5 years, when we'll be able to build sufficiently big quantum computers to build quantum random access memories to load and embed classical data into quantum systems so that we can realize the power of quantum machine learning.
So that was released 5 years ago, so that was an optimistic figure even 5 years ago. But why not?